Hello everyone. So welcome to IIT and Gate classes. So this is a video series on gas dynamics topics. So today's topic will be seeing about speed of sound. So that's a very important topic. So let us see what is speed of sound looks like. The definition of speed of sound, or how can we arrive at an expression for speed of sound. Okay, so I'm Akshay. So you are faculty for this gas dynamics course. Let us jump into the definition. So before going forward to define what is speed of sound is all about, so I want to bring in some of the concepts that is needed to be understood to understand the idea of speed of sound. So the first of all, the compressibility. So the compressibility is defined as a partial derivative of a specific volume with respect to a pressure, right, at a given volume. So as a flow approaches a velocity comparable to the uh, velocity of a sound in a medium, so the effect of compressibility becomes more and more important. So that is why idea of compressibility is uh, important to understand, right? So we can define a compressibility either in isothermal uh, uh, process or through a isentropic process. Before going on to define a speed of sound, we have to remember like earlier days when people thought of how sound travels in a medium, or how can we hear things, right? So people thought the, the speed of sound is somewhat related to a molecular idea. That is true to some extent, because if I go back and check my idea of kinetic theory of gases, we have average kinetic, average speed of molecules is a function of, so if I define velocity from a kinetic idea, so average molecular speed is somewhat proportional to square root of r and t, right? So there's a constant. Obviously, there's some other constant comes into picture. So, but it proportional to the temperature. So if I see back expression of sound, so that is almost a velocity of sound. If I denote by a, it is also proportional to root of temperature. So that we will see later, and it is a comparable fraction of this one. So it's about 3/4 of a molecular velocity. So that is true. So what people have thought is a speed of sound is essentially the way how a sound wave propagates in a medium is essentially following an isothermal process. That's what they assumed in the first place. But when they compared with respect to experimental results, they were not quite able to replicate the results what they have arrived from a theory, because they assumed, all importantly, they assumed isothermal way of defining speed of sound. Later, they realized that it is not exactly following isothermal compressibility. It's actually following isentropic compressibility. When they did that correction, so they were able to get the speed of sound expression that exactly matches with the experimental results. So that is where the idea of this different thermodynamic process plays an important role. Right. So as I said that, uh, as I already said this, compressibility is a property of a fluid, just like any other properties like pressure, temperature, or density, like that, different properties of a fluid. Compressibility is also a property of fluid, right? It depends on different fluids. Like for water, it is different, and for air, it is different. For other gases, it might be different. So compressibility is a property of fluid. And as I said earlier again, so when the fluid is flowing, the effect of compressibility plays a major role as fluid velocity approaches a comparable fraction of velocity of sound. So that means like Mach number, if I define that is non-dimensional number defined as a local velocity of a fluid to a local velocity of sound. So this approaches a comparable fraction of sound. That means if Mach number becomes greater than 0.3, so then effect of compressibility plays a major role. So we have to account for compressibility effect. So usually we assume with incompressible medium and we do calculations. So the moment when I cross m greater than 0.3, my calculations start showing error if I assume incompressible model. So we have to account for compressibility to make sure our answers are accurate, right? So then other aspect is like the study of thermodynamics, which is very much fundamental to understanding the compressible flows because of the effect of compressibility which comes into picture, and which brings in a new variable in the form of energy equation, that is thermo temperature. So understanding of thermodynamics becomes important. Okay, so keeping these fundamental ideas in mind, so let us move on to define the speed of sound. So here we have to see the left figure, whatever we are having here. So this is the actual scenario where a sound wave which propagates in a stagnant medium. So that means a wave is propagating with a velocity A on a stagnant medium, where condition for stagnant medium is a pressure P, temperature T, density rho, right? So the moment when a wave passes through a medium, so it immediately behind the wave, the properties will change, right? It's kind of a weak shock wave. We can treat in that way. It's a weak shock wave. Across the wave, there is a change in properties. So there is a change in properties, like the P becomes P plus dP. So there's a small change in pressure, the small change in temperature, the small change in density. So what we are going to do is like, we are going to fix the frame of reference so that wave is now fixed. Instead of wave moving at velocity A, we will treat the same scenario such that the medium is now traveling with the velocity A and wave is fixed, across which again the properties will going to change. Right, so this is similar to how we mimic the experiments in a wind tunnel, right? Like we want to study the aircraft which is moving in the air. Instead of doing so, what we do is like we will fix a aircraft in the wind tunnel and we will allow the streamlines to follow, right? So that like it's relatively the same. So whatever the forces or whatever the results we are going to extract from this experiment is mimicking the flow physics when the aircraft is moving on a still air. So same idea over here. So we are keeping a stationary wave with a medium which is moving towards the wave, right? So again, across the wave, there is a jump in properties here. T is going to change as T plus dP. T is going to change as T plus dt. Rho is going to change as rho plus d rho. And a speed, that is A, is going to change A plus dA. So this is unique now, right? In the initial case, we have the constant wave speed that is moving on a still medium. So A is what we are treating as a velocity of a wave. Now we are keeping a wave constant. So that means the fluid which is approaching at velocity A now will change to A plus dA once it crosses the wave, right? It's downstream of the wave, right? So now our idea is to analyze on this system. So we will use a control volume analogy. So I have a stationary wave. If I draw a control volume, right? Right. So if I draw a control volume where wave is sitting inside, so R, I am interested in what's coming in, what is going up. So here I have properties rho, T, P, A, and once it goes out of the control volume, I have rho plus zero and T plus dt, P plus dP, and A plus dA, right? So importantly, we have to understand here. So all we are treating is one-dimensional flow. I have a velocity vector that is just a in the x direction plus all other component v and w. They are the j direction and k direction. They are going to be 0. So I'm treating only one direction. So where a is the x component of velocity. So if I have a system like this, x, y, and z coordinate system. So I have only x directional variables. Other direction, I'm treating the variables are not going to change, or uh, the variables, whatever I'm interested in, they are a constant in any other direction other than x. Okay. Now, if I apply the continuity equation on this control volume, what happens? So I have my continuity equation that is conservation of mass, right? System which is equal to 0, that is equal to dou by dou t integration over a control volume rho dv plus I have a control surface integral of a flux, that is rho times v dot area vector, right? So now you see we are treating this system to be a steady. So I can omit this term. So that means I left with only a flux term. That is integration over a control surface rho v dot ds equal to 0. So if I apply the Gauss divergence theorem, so I can write in terms of del dot or divergence of rho v equal to 0. So, right? So I'm not showing all the steps because we already did this in our previous classes. So now, because it's a one-dimensional system, that means I have velocity which has only one component, that is in the x direction. So if I do that one, what do I get? So if I expand this term using a vector operator, so that becomes rho times divergence of velocity plus velocity vector times gradient of density. So divergence of velocity, that is rho times dou by dou x of a. I have only one component. Similarly, a times d rho by dx. All other component which comes out of a gradient, which is going to be 0 because I have other component of velocity which is multiplying. Those other two components are 0. So I just left with this equation, right? So if I really put into this way, so this becomes rho dou a by dou x plus a dou rho by dou x, which is equal to 0, or I can write it's just a differential equation, that is dou rho a by dou x is equal to 0. So what does it say? So whatever which is inside the differentiation, that means this is nothing but rho a is equal to constant, right? This is important. So from continuity, we got that rho a is equal to constant. So if I use that idea between two control surfaces of control volume of our interest, that is rho a is equal to rho plus d rho, that is at the exit of the control volume, times a plus dA, right? So now if I expand that one, rho a is equal to rho a plus rho dA plus a d rho plus d rho dA. So what I'm going to do is like this term get cancelled. So all the higher order terms, like because change in density and change in velocity is a small quantity and multiplication of two small quantities will be even smaller. So I'm going to neglect all the higher order terms, which is the second orders. So if I neglect that one, so I'm left with rho dA plus a d rho, which is equal to 0. Or what I can write is, I can write for a. A is nothing but minus rho dA by d rho, right? Because it's a one dimension, so I'm omitting the partial derivative thing. I'm just keeping it as a normal derivative. Or given that it's a one dimension, I can write like this. Okay, so this I will call it as equation 1. So that is the result of momentum equation, or I can also write for dA. So dA is nothing but minus a d rho by rho. So I can write it anyway. It's fine, right? So now I go back to my control volume again, apply the momentum equation, right? So again, it's a one-dimensional momentum equation we are looking at. So it's a 1D flow. So what my momentum equation says is dmv divided by dt, the linear momentum is conserved, right? This is equal to summation of the force in this system. So in this case, I am considering in the x direction, right? So that is equal to, again, rho by rho t of volume integral of rho v dv plus surface integral of rho v dot ds times v, right? So owing this is a steady state, so this goes to 0. All I left it rho v dot ds v. So I know it's a one direction because v has only one component. So that becomes divergence of rho a, right? So rho a times velocity vector equal to minus rho p by rho x, right? So in x direction. So again, v is nothing but velocity. So where it has only one component, but let us try to expand it. So if I expand it, so I get this form, right? If I take a common, or if I split this one, a and rho v as a two different variables, so that becomes divergence of rho v plus, if I take rho v dotted with gradient of a component of velocity, so minus rho p by rho x. So now you see, this is nothing but a continuity equation. So from continuity equation, I know divergence of rho is 0. So all I left with rho v dotted with gradient of a. This is equal to minus rho p by rho x. That's interesting. And what is this one? So this is v dot grad a. So that is nothing but rho times a times dA by dx, right? So because I have only one component velocity, so that is equal to minus rho p by rho x. Interesting. So now you see, can I write this rho a times dA dx in some other form? So let us try to explore that. So what is that one? So I can write in the sense that I can write d by dx of rho a square, which is equal to rho into d a square by dx plus a square times d rho by dx. Same thing, right? So, or what I can do, instead of rho a square, I can take rho a common over here, right? So rho a times dA by dx plus a times d rho a divided by dx. That's also fine. So I can write rho a times dA by dx is nothing but rho a times dA by dx is nothing but d by dx of rho a square minus, so just using rho a times d by dx, minus a times d rho a by rho x. What is this one? D rho a by dx. From continuity equation, we know that if I go back and see my continuity equation, what is this one? Dou rho A by dou x is equal to 0. So I can put this term going to be 0. That becomes d by dx of rho A square. So I can replace over here rho A times dA by dx. I can write in terms of d of rho A square by dx equal to minus dp by dx. Again, I am writing partial derivative in terms of normal derivative because it's one direction, it's fine. So now you see here, I can write d by dx of rho A square plus p equal to const 0, right? So this is 1D momentum equation, right? So now you see, if this is equal to 0, that means rho A square plus p equal to constant. So this is important result now. So I can apply between two phases of a control volume where a flow is entering and flow is exiting. So it has to be constant, right? So that means I have p plus rho A square at the entry and p plus dp times rho plus d rho times a plus dA square, right? So this has to be true now. So now if I expand this one again, it is p times, sorry, plus, right? So I have p plus dp plus rho times, if I use a plus b whole square form, that is a square plus b square, that is dA square plus 2ADA, right? So I use that one, that is rho times a square plus rho times dA square plus rho times 2ADA times 2ADA plus d rho times a square, that is a square d rho plus I have d rho times dA square. Again, I have d rho times 2ADA. So that is 2ADA d rho, right? So now you see, again, I am doing the same thing. So from left hand to right hand, dp get cancels, rho A square, and I have rho A square that cancels, and all the higher order terms I'm neglecting. This dA square, that is dA d rho cancels, d rho dA square cancels. So all I left is now dp plus 2a rho dA. What else I have? Yeah, plus a square d rho. So that is equal to 0. So this is what I left. Okay, so now what I can do, I can write a square one side, this term one side, that is dA one side, all other terms, minus dp plus a square d rho whole divided by 2 times rho into A. So this is what I left with. So now this is my equation 2. So if I go back and check my equation 1, so I had from equation 1, that is, I had a term for dA, right? dA is equal to minus A d rho by rho. So I can replace that in equation 2. So that becomes minus A times d rho by rho equal to minus dp plus a square times I had d rho whole divided by 2 times rho times a. So rho and rho get cancelled. So all I left is minus of minus, that becomes plus. So that becomes 2 times a square d rho equal to dp plus a square d rho. Interesting. So now I can write for a square. So that turns out to be a square is equal to, this is a square d rho. So that is dp divided by t rho, right? Or I can write A is equal to square root of dou p by dou rho. So I have to treat it very general way. So, and I know the speed of sound is following, the sound wave is propagating such that it's following an isentropic process. So at constant entropy, this is my expression for speed of sound. But how can we relate it to temperature? So that's what we started off the questioning. Can we relate it to something related to kinetic theory? So where it says that average molecular velocity is a function of temperature. So can it be the same with the speed of sound? Of course, we can show that because we know for isentropic process, we know p by rho to the power of gamma is equal to constant. So or that is nothing but p is equal to constant times rho to the power of gamma, or dou p by dou rho is nothing but constant times gamma times rho to the power of gamma minus 1, and c is nothing but p by rho to the power of gamma times rho to the power of gamma minus 1. If I take LCM of this one, so I will get p by rho times gamma, right? So that is nothing but dou p by dou rho, yeah, isentropic process. So just replace that one. So what I left with, A is equal to square root of gamma p by rho, right? Right? So that means I can now show that for a calorically perfect gas, I have P is equal to rho RT. What is P by rho? P by rho is nothing but RT. So I can replace that one with A is equal to square root of gamma RT. So this is the well-known expression we might have used multiple times, right? So this is a function of temperature, the speed of sound. And I can go on and show how it is related to a compressibility, right? So I have a definition of compressibility tau in a isentropic process that is nothing but 1 by V times dou V by dou P, or I have V is equal to 1 by rho. That means dou V by dou rho is equal to minus 1 by rho square. So if I replace dou V with this expression, so that becomes 1 by rho times dou rho by dou P. So this is defined for a constant entropy process. So if I replace that one, that becomes dou P by dou rho at constant entropy is nothing but 1 divided by rho times compressibility. So I can replace that one in my speed of sound expression. That becomes square root of 1 divided by rho tau s. Now you see, if compressibility increases, the coefficient, so this is a compressibility coefficient, so it increases, my speed of sound decreases. So it has a direct relation. The gases which are more compressible, that has a lower value of speed of sound. That means like speed of sound travels faster in denser medium compared to uh, uh, the medium which is sparse, or the speed of sound is more where a medium has a lower compressibility values. That is like in water, the speed of sound is more. The water is less compressible liquid, right? Compared to less compressible fluid compared to air, whereas air has a lower value of compressibility value, but it is highly compressible. That means in a higher compressibility value, that means the speed of sound is less in air. So that makes sense, right? So it's inversely related to compressibility, so it makes sense. So this is speed of sound in general I wanted to discuss. So we are well known with this expression, but the idea what we have to connect here is like how we can approach from macroscopic point of view. That's like we applied a control volume approach that's purely applicable on a macroscopic point of view, like we treat a fluid as a continuum medium, whereas the speed of sound is something, the concept which comes from a microscopic point of view. As I said earlier, it has a relation to kinetic theory of gases, where we can say like it's almost 3/4 of this average molecular speed. The idea of temperature itself is a microscopic point of view, but still we treat it in a macroscopic terminologies, and we can still arrive at expression for speed of sound, and it's exactly matches with the experimental results. So this completes my our discussion on speed of sound. And for more information, you can contact us. So at iitiansgateclasses, and we have started our crash course for GATE 2023 from November. You guys can free to inquire us. Thank you for listening.